Zero-knowledge privacy starts with a simple shift. Prove what matters, without exposing everything behind it. In this section, we'll see how selective disclosure, private state, commitments, nullifiers, and eligibility proofs turn sensitive data into verifiable claims. We've built from scaling to ZK rollups. Now we shift the focus from using proofs for efficiency to using them to reduce what blockchains expose. Zero-knowledge privacy is not magic invisibility. It is controlled disclosure. Rather than handing over a private document, the user generates a proof that the document satisfies agreed rules. The verifier can trust the result, such as, yes, this person meets the requirement, without seeing the birth date, account balance, or other sensitive input. That separation supports identity checks, compliance, access decisions, and financial workflows where proof is needed, but exposure is not. A ZK privacy flow separates what must be proven from what must stay hidden. The user begins with private data, such as identity details, balances, or eligibility facts. A proof generator uses that data to create a cryptographic proof. Only the proof and a public claim are shared, such as, this user is eligible. The verifier checks that the proof is valid without receiving or reconstructing the underlying private information. Selective disclosure changes the question from show me your data to prove the one fact I need. A user does not have to reveal a passport, location history, or bank statement. They can prove they are over an age limit, in an eligible region, or above a minimum balance. Zero knowledge makes that proof trustworthy without exposing the underlying records. The result is less data collection, less stored sensitive information, and privacy built into the application by default. Threshold proofs answer a narrow question. Does a private value meet a rule? Rather than sharing a birth date, full wallet balance, or exact credit score, the user proves only that they pass the cutoff. The verifier gets a yes or no result. That is powerful when eligibility matters, but the underlying number should stay private. Credentials let a trusted issuer make a claim about a user. Over 21, a citizen, accredited, compliant, or a member. The user keeps that credential private and uses it as an input to a zero-knowledge proof. The verifier does not need the whole document. They learn only that the required attribute is valid and that the issuer's attestation checks out. This turns identity into reusable, privacy-preserving access logic. Commitments solve a key privacy problem. How can a public system rely on private data without seeing it? A commitment is like sealing a value in an envelope, often with added randomness. Everyone can reference the sealed envelope, but they cannot read what is inside. Later, a proof can show that the hidden value has a valid property without opening it. This is why commitments are fundamental for private payments, voting, and confidential application state. In application design, commitments act like privacy-preserving placeholders. Instead of publishing a user's balance, note, or identity attribute, the app publishes a commitment. Later, the user proves they know the hidden value and that the requested change follows the rules, without exposing the value itself. Validators check the proof, not the secret. That is the bridge. Public infrastructure enforces correctness, while private data stays with the user or application. A nullifier is a one-time public receipt created from private data, such as a vote, withdrawal, or eligibility secret. A zero-knowledge proof shows that the receipt was generated correctly, but not who generated it. The system asks only one question. Has this nullifier appeared before? If not, the action is accepted and recorded. If it appears again, the duplicate is rejected. That is how privacy and one-time use can coexist. Encryption and zero-knowledge are complementary tools. Encryption keeps data unreadable, even if it is stored in a public place. A ZK proof lets someone verify a claim about that data without opening it. When certain people need more detail, viewing keys or permission rules can grant selective access. Together, these tools support privacy for users, evidence for auditors, and trust for applications. Eligibility proofs let someone pass a gate without handing over the whole dossier. In a private DAO vote, the user may hold a membership credential or required token balance. Their wallet generates a zero-knowledge proof that the rule is satisfied. The DAO verifies the proof, accepts the vote, and never learns the voter's real identity or unrelated attributes. The same pattern works for allow lists, financial access, location rules, and compliance checks. Identity proofs are one of the clearest uses of zero knowledge. A user proves only the fact an application needs, rather than sharing an entire document. Membership proofs show someone belongs to an approved set, without naming them. Attribute proofs confirm requirements like age or residency, without exposing the full ID. Compliance proofs show that a screening was passed, without revealing every detail. The result is trusted access and onboarding with far less personal data collected. Zero-knowledge proofs can let a financial institution make a strong public claim, such as assets exceeding liabilities, without exposing every customer balance or trading relationship. That can give investors and counterparties more confidence, while preserving privacy where raw records would be commercially or personally sensitive. But the proof is only as useful as its scope. Which liabilities are included when the data was captured, and what assumptions prevent hidden obligations from being left out. The core privacy lesson is simple. Do not collect and inspect everything. Use ZK to verify only the fact the verifier needs. Selective disclosure, commitments, nullifiers, and encryption make that possible across identity, compliance, finance, and access control. Next, we'll see why ZK rollups still need explicit privacy design.